All right, we're getting closer to do an example here. Let's start with the topic we typically start with when we're looking at brittle type material, and that's flexure. So a lot of this is going to look a lot like concrete, a lot like concrete. The biggest difference is we're looking at allowable stresses instead of ultimate case, right? So instead of, if I just look at concrete by itself, and I know it goes like this is a stress strain curve, or you can call this little f. And stress strain, when I do this for concrete design, this is essentially at ultimate, and I turn that into a Whitney stress block. Right, that's how I get this thing. This is essentially the concrete stress at ultimate, and I have a crushing strain, and I have some slides on this. Now I'm only in what's fairly much in a linear elastic region. Okay, I'm not going to go into this whole crushing piece. So I wanted to put that out there first because it gets a little confusing if you just try to look at some of the stress diagrams that are in these slides. The key is I'm in the linear elastic range, and so I'm going to still have tension and compression, but I'm going to be looking at a different point along the curve here. Okay, so it's a difference between allowable stresses and looking at ultimate along with some serviceability pieces that we do in concrete. All right, so let's get started. So I got to do the overview here of the basic concepts before we get into our example problem, which will be a separate video. So bear with me here. Stresses are linear elastic, right? Stress strain. Plane sections remain plane. You've heard that plenty of times. Stress is proportional to strain. Modulus elasticity is constant throughout the member, okay, so don't have changing properties. No tensile in the masonry, just like in the concrete. The span of a general flexural member is going to be large compared to the depth, right? The differences in shear walls, which are a whole different beast. We will deal with flexure, but we'll deal with a lot more shear in those. So generally, if I'm doing a pure flexural type member, it's a beam. All right, so we assume that we put all the masonry elements together. So we've got those hollow sections. I'm talking about the CMU basically now. So I've got the CMU, it's filled with grout, I've got some reinforcement in here, but we're going to assume that it's all smeared together, acting as one unit, which is reasonable during normal working stress levels. I showed you like, oh, I can crack along the joints, and I was talking about in your basement, you could have the masonry block walls, and you might get cracking along these joints from shear or something like that. I'm no longer linear elastic there, right? I've gone into failure of that joint, so it's cracking. So as long as this is all one uniform piece, it's actually pretty homogeneous or homogeneous. At high stress levels, a lot of this is not going to be practical because now stress, I've gone past this and it's no longer proportional directly to strain. We're going to stay in that early section. Okay, working stress, which is how these are designed. It's all good. If you go and work in California, you're going to have to deal with a lot more seismic issues, and that it's a different concept. If Dr. Hedegaard teaches the structural dynamics class and you're still at UMD and haven't taken it, that's a good baseline for taking a future seismic design class. Okay, so external and internal moments and forces are all in equilibrium, so equilibrium as always. We're going to use straight uniform cross sections. In other words, we're going to use normal beams, not tapered beams or anything crazy. Similar flexural theory compared to reinforced concrete. Okay, compression at the center of the compression block. Okay, in the CMU, that's typically in the face of the shell, right? So if I look at, here's my deal. The face of the shell is here, and so right in the center would be the compression piece, right? That's what they're try to say, depends on which way this is oriented. Could be this way, right? Okay. Tension is at the center of the rebar. Typically, that's at the center of the wall. Masonry carries no tensile stress. Stress is proportional strain. D is the distance from the extreme compression fiber to the extreme tensile fiber. So if I just make my masonry beam, whichever direction it's going to be, I've got a compression block and I've got a tensile block, and extreme compression fiber to the center of tension is still D. So let's put all these guys together. You've seen this, concrete flexure. This is at ultimate. That's why we've got this block, right? So it's actually, this is A, this distance would have been little c, right? And the actual diagram looks more like that. There's a steel. I go to crushing strain and yield here. Why? Because I'm looking at ultimate. Not going to happen for masonry. So what do I have here? Now I have a nice linear stress strain curve. So I'm going to stay in the linear region. So I don't need the block because I don't have to approximate some weird parabolic shape. I just have a triangle. So you can see where that's going to act, right? The 2/3 point. Here's my bending stress. Okay, and we'll talk about this, and the stress in the masonry. And the TMS has those limits, or those values. This is still D. Right here, actually. That's still D. And then the distance from the centroid of here to the steel is a factor J times D. If you had learned concrete at another, a long time ago, back when I was a student, I didn't learn it this way, but a lot of people were still teaching it this way, and a lot of designers were still doing this. This is also something that they'll do to design concrete. It's just a percentage times D. Now in concrete, it acts at a different location. So what we're doing here for masonry, for some designers, particularly ones who are a little older like myself, you'll see this JD thing creep up in their calculations. If you see that and you're checking, you're going over work or using some old calcs as an example, you'll actually know what they're up to because that's how we're going to do the masonry. A lot of that's left over from looking at allowable stress design. Now, concrete's been LRFD for a long time, but there is some folks who look at the allowable stress piece for masonry and do something similar. So I can do JD for concrete too, but in that case, it would have to be a JD that goes same difference, but it's at ultimate. So anyway, don't worry about that. This is what we're going to do for masonry. So JD is defined that way. This distance, KD, is essentially the same as little c for concrete. All right. Now, this triangle goes all the way down to C. I don't have an A, little a, because I don't use the block. Stress for steel, 32 KSI for grade 60. Okay, that's the allowable stress that we're going to use, and we'll get into that in the example. All right, so it's still true that moment is C times the moment arm equals T times its moment arm. Right, so the D minus A over 2, all the stuff we've done for concrete, these things are still true. I'm just going to use a little bit different terminology. So we've got the KD I showed you on the other drawing. The K is the portion of D which is in compression. Okay, so it's just giving me the percentage of D that's in compression. Moment arm in concrete, D minus A over 2 is now just JD. It's some percentage of D. J is that coefficient. F sub B is the bending stress in the masonry. F sub S is the stress in the steel. And those, because we're linear, are just strain times modulus. So that's pretty handy. This is actually, it's different because you haven't done it before, but it's actually easier than what we do in concrete. Okay, so concrete versus CMU, some differences. No crushing strain or yield because that's ultimate. Allowable stress. And we put limits on the masonry and steel bending stresses, or the stress in the masonry bending, and the tensile stress in the steel. So we don't have that crushing piece. The compression block is rectangular in concrete versus, so we're not doing concrete, we're doing the triangle for masonry. Okay, hopefully I didn't confuse you a lot there, but we're going to do problems. Okay, so flexural compressive stress, tensile stress in steel. There's the ratio of these two strains will come in handy, right? And if I write those out, I will get KD over D minus KD. Modulus of steel is still 29,000 KSI. Modulus of, or the elastic modulus for masonry, remember we have in ACI, we've got a square root and all that. Here we've got a coefficient of 900 times F prime sub n for the concrete stress in the masonry. And the handbook and the code will be where we take a look for that. So again, in the example, that'll make sense. We do want to look at module ratio, which you've talked about back in the mechanics class, and we've talked about from time to time in other classes. And so in our case, N is going to be defined as the modulus of the steel to the modulus of masonry. Okay, so the bigger on top, so it's a number greater than 1. So I transform the steel into equivalent masonry. So if I have a block, so if here's my masonry, I can't count this in tension. So I've got this block of concrete. I've got this bar of steel, or not concrete, masonry. I'm going to transform that steel so that I end up with compression masonry and equivalent tension masonry. Okay. We do this to figure out where the neutral axis is. So in, well, this is easier to find the neutral axis when we're doing this. In concrete, we're calculating an A term and some other different things. Here, I actually want to know where the neutral axis is, okay, which we could find in concrete too, because A was related to little c, which was the distance to the neutral axis. So bear with me, we'll do that. But you did a lot of this when you were in your mechanics class, hopefully. And you probably even did examples with concrete. You may have done some of it in reinforced concrete if you were looking at deflections. All right, so we've got an example here. Okay, with some, they've cut through some of these blocks here, but here's a section of masonry block. A lot of times we're going to be dealing with a section of wall, but we're going to start out with flexural, just pure flexural members. This is my transform, so N times area of steel. That modular ratio times area of steel is going to give me the transformed steel. Okay, here's my steel. Here's my overturning moment, D minus KD and KD, right? So this is my compression block, this is my tension block, or tension force. Neutral axis is at KD, okay? And what is that? That's where the compression is balanced with the tension, okay? Determine the neutral axis by solving for the KD at which the compression equals tension. That's it. Okay, so if I go through this, I'm going to get C, which is KD times the width B, right? This was, when we used A, it was the same thing, but now our block is KD by B, so that's my compression force. Okay, the moment arm is KD over 2. Okay, so the distance there is KD over 2. And over here, I've got the tensile piece times the moment arm. So so AS is B times D. We'll talk about these two terms, but that's my modular ratio piece. Okay, so I'm going to have that as my tensile force. And then I need D minus KD. Sorry, didn't mean to draw that. D minus KD takes me to the center of the steel reinforcement. Okay, so that's that moment arm. 2 moment arms, and then these are the forces. All right, so simplify that. You get a quadratic. You use the quadratic equation to solve for k. And if you want to actually solve for k, you're going to get this as the equation. Okay. It's always what it's going to be for this type of single reinforced section. But the rule of thumb is you start out with a k about 30%. So that'll come into play when we're going to design from scratch. Okay. So hang on just a second. It's the same thing we just looked at. In this case, approximating the triangular stress block, and we just said that K is approximately 0.3. Okay. So what we find is the length of the moment arm, JD, right? This is the moment arm between the compression and the tension. Okay. And that J is the coefficient that tells us what percentage of the total height this is, or what percentage, you can also think of as the percentage of D to the bar. If we use this as a triangle approximation, we know that J is going to be 1 minus K over 3, and the rule of thumb for J is that it's about 90%, which makes some sense. Okay. So I'm going to use these two rules of thumb with K and J, and particularly J, to go ahead and proceed, particularly if I'm designing a section from scratch. All right, so moment capacity. Now I'm looking at the actual capacity of the section. For concrete, we always say it has to be under reinforced. If you took concrete with me, that's the first thing I quiz you on. We want it under reinforced because we want ductility. It's over reinforced or not reinforced, then I get brittle failures. So I want the steel to yield before concrete crushes. Masonry is not the same. Okay, so we don't worry about this. We can design it as over, under, or balanced, which that's kind of fairy tale land, but it can be around the balanced area. It's usually typically one or the other. The allowable moment of the section is the lesser of the two moments you calculate from these two cases, the steel version controlling or the masonry version controlling. That's the S and the M. Okay, so over reinforced means we're controlled by the allowable compressive stress in the masonry. So I want the moment based on the masonry stress. That's going to be C times the moment arm. Okay, so here's my F sub B. So C, half base times height, right? Here's my stress times JD, it's the moment arm. And this is my formula for the moment in the masonry. Under reinforced is when the steel controls. Same deal, ASFS times JD, this guy. And this is the formula that controls for steel moment. All right, balance as if they happen to, or that they're exactly the same. Yeah. And if you round to the nearest kip inch or something, you can get a balanced situation. All right, so just like in wood, big F sub B is the allowable flexural compressive stress, and big F sub S is going to be the allowable, like in wood, the capital F is what I meant, the allowable tensile stress. So bending masonry and then steel. TMS allows 0.45. Okay. And then over here, we're allowed 32,000 PSI for grade 60 steel. So that's what we're going to compare to. Okay, so I'm going to stop here because what we're going to do is do the first example. Okay.